Hello, welcome to this presentation on Segment Anything. My name is Dylan Ditta. I am an electrical engineering undergrad and computer engineering graduate student. I am here to talk about the Segment Anything application, an application that can turn any image into a set of masks with descriptors that can be very useful for prompt engineering applications. As we know, as academics in the study of deep learning and neural networks, one of the most odious aspects of our craft is obtaining and refining an applicable dataset for our model. An obvious example of this would be an image database with labels, something we're very used to with convolutional neural networks. Let's say that you need to create a model that learns how to detect every tennis ball in an image. First, you would need to detect that there are round objects in that image. Then, you would need to detect that those objects are tennis balls, etc. The Segment Anything application aims to attack this problem by creating a way to automate the detection of unique items in an image and apply masks to them. Further, the application will also attach labels to those objects automatically without prior knowledge. With this model, we aim to solve a range of downstream segmentation problems on new data distributions using prompt engineering. Prompt engineering is defined as the practice of designing inputs for AI tools that will produce optimal results. Prompt engineering makes it easy for users to obtain relevant results in the first prompt. It also helps mitigate bias that may be present from existing human bias in the large language models training data. The Segment Anything team released the SA1B dataset for research purposes and making SAM available under a permissive open license at the link provided. So, what did these authors accomplish? The Segment Anything team has created a large, diverse dataset of 11 million images with over 1 billion masks and labels with a high resolution that will be publicly available. The team has also created promptable segmentation, a task which allows a user to generate a mask from any image given a prompt from the user for what they are trying to identify is in the image. In Segment Anything, the zero-shot method of analysis becomes important. Zero-shot tasks are those that are able to perform well on tasks they were never trained on. For example, a model trained on making masks over grapes in a garden image will also be able to make masks over spaceships in NASA without having seen either image before. Zero-shot tasks give the ability to apply the model from one image and task to another image and task without related knowledge. An increased focus was placed on responsible AI, so the biases against marginalized groups are to be minimalized. As we can see in the figure, most of the world's countries have images numbering well over 1,000. However, North America and parts of Europe can be seen as having 100,000 images or more on average. Poorer countries, however, tend to have less than 1,000 images on average, and as a result represent 0.9% of the world's samples. This shows a misrepresentation of these groups in the overall data. SAM attempts to mitigate this problem by achieving an average of 9 million masks more than the other segmentation datasets. The main novel achievement that SAM accomplished over all segmentation is the ability to segment from any image what is described in any prompt by zero shot. So how did they improve upon this competition? The final dataset, SA1B, includes more than 1 billion masks from 11 million licensed and privacy-preserving images. SA1B, collected fully automatically using the final stage of our data engine, has 400 times more masks than any existing segmentation dataset. So mask quality. Mask quality must be estimated through randomly sampling 500 images, which means 50,000 masks, and then asking a team of professional annotators to improve the quality of all masks using simple brush editing tools. Comparing SAM to other annotation algorithms such as COCO, AID20K, and OpenImages see SAM outperform other datasets in number of masks per image, achieving what was set out to be done by the team. Images in the SA1B library are diverse in both ethnicity and financial background, as we discussed before. The objective of creating a novel distribution of data that could be easily generalized made it important to train SAM on a large, diverse set of masks, far greater than anything that currently existed in segmentation datasets before SAM got to it. So the typical way of gaining segmentation data online cannot be approach chosen. Therefore, a data engine needed to be built in order to solve this problem, and needed to be developed in tandem with the model through a model and loop annotation strategy. Even after downsampling, these images are significantly higher resolution than many existing vision datasets, like COCO. The problem can be defined in three parts: the task, the model, and the data engine. Once those three problems are solved, then SAM is complete. So the task. Based on the accomplishments of natural language processing and computer vision, the objective is to perform zero-shot and few-shot learning for new datasets by using prompting techniques. And our goal is to return an application segmentation mask given any prompt, or their goal was, even those not necessarily in the image. So the model has three main parts: the image encoder, prompt encoder, and lightweight mask decoder. The image encoder computes image embedding. A vision transformer is minimally adapted to process high-resolution inputs. The image encoder runs once per image and can be applied prior to prompting the model. The prompt encoder embeds the prompt. We consider two sets of prompts: sparse, which are points, boxes, or text, and dense, which are masks. We represent points and boxes by positional encodings, summed with learned embeddings for each prompt type, and freeform text with an off-the-shelf text encoder from Clip, which is by OpenAI. Dense prompts, or masks, are embedded using convolutions and are summed element-wise with image embedding. The mask decoder efficiently maps the image embedding, prompt embeddings, and output to a mask. The mask decoder block uses prompt self-attention and cross-attention in two directions: prompt to image embedding and vice versa, to update all embeddings. In order for the SAM team to accomplish what they wanted, it must be trained on a large, diverse dataset of masks which did not exist at the time. Therefore, a data engine must be built, which was concurrently developed in tandem with the model and the dataset. There are three stages to this data engine. First is the assisted manual, where SAM assists annotators in annotating masks. Then semi-automatic, which is where SAM automatically generates masks for some objects and annotates for others. Finally, fully automatic, which has SAM generate most masks in an image. And now I'll switch over to Kaggle to go through my code example. To go through what needs to be done in order to use segment anything for your code. First, this is what I used. What you need is to find a data set that has a test folder and various folders for the names of the objects that you're testing for. I happen to use gemstones for my test. We need to import our libraries, import install our libraries, import our libraries. Here we pre-process the data, going through all of the different paths and initializing them. Then we initialize our data loaders. We go through all of the training directory and the test directory for our data set, do transforms on them, and then make our data loaders. Then we need to initialize the model. This is all taken from the Segment Anything official model using the Vision Transformer 1 model type. Okay. So then we take a subset of the images, do our training based on that, and then we take a particular image that we want to segment. For this, I chose this image. And then you plot it, and you can see that Sam segmented out the different lattices in the crystal structure, in the gemstone structure. The original idea that I got this tutorial from used sports image classifier. I believe it's this one. Why won't it come out? Okay. Yes, it was this one. And I'll quickly go over that to show how you could take a new data set. So here we have a new data set, the sports classification data set. All you would have to do is change the name from my gemstones data set to sports classification. And then you would need to take a particular path and do it that way. So we're going to do the test data set. Well, maybe not the test data set. Yeah, the test data set. For sports classification, test, air hockey, and this one, and it should be able to run. Okay. And there we go. That's how you do it.